All right, a linear function has the same slope at all of its points. That's why it's linear. That's basically the definition of a linear function. All of the points are in the same line, so they have the same slope. But nonlinear equations will have different slopes at different points, which brings up the concept of a tangent line. Remember, a tangent line is a line that intersects the graph at one point. You're probably most familiar with tangents to circles, and we can just start with that. So if you have a circle, I was doing really well, and then I completely botched it up. Then a tangent to the circle is going to be a line that intersects that circle one time. Well, the slope of the tangent line is the same as the slope at the point of tangency to the graph. So does a circle at all of its points, does the circle have the same slope at all of its points? No, because here I've got one slope. It's obviously a positive slope, but if I were to go up here, it's a different, and it's even a negative slope. So, and you can see that any, I know, I'm not doing very well here, but this thing is kind of hard to write with. If you have, say, a cubic polynomial, then if I wanted to find the slope at any point on that polynomial, I would find the slope of the tangent line at that point. And the slope changes at different points on the graph. All right, so the question is, how do we find the slope of the tangent line? What we do is we're going to approximate the slope of a secant line by choosing points that are closer and closer to the point of tangency. Well, a secant line is a line that intersects the graph in two places. All right, so I'm eventually going to try and find my point of the slope of the tangent line at x equals c. But I'm going to have to use a second point. So I'm going to call this c plus delta x. And the reason I'm using delta x is that's just change in x. So I've gone away from c, some change in x value. All right, well, to find the slope between 2 points, I want to use my slope formula, which is just difference in y's over difference in x's. So I need to actually name these points. If this is the graph of f of x, and this is the x value c, how could I name that point? C, comma, f of c, right. All right, and how could I name the second point right here? Good. Okay, I'm going to attempt to draw a line through those points. I think that's pretty good. Okay, so let's find the slope. All right, so slope is difference of y values. So I'm going to take f of c plus delta x. What? And then I'm going to divide by my difference in x values. So my two x values are c plus delta x minus c, which the bottom can definitely simplify to just delta x. Now, what I want to do is I want to methodically move this second point closer and closer and closer to C. Because if I were to move that second point right here, then there's my new secant line. And what I'm ultimately trying to approach is the tangent line. Here's my tangent line. So when I move this point closer and closer and closer, then this big old googly part of blue lines starts approaching that red line. So what I want to do is I want to use some concept that we learned in Chapter 1 to do this. What am I wanting delta x to approach or become? 0. And what's that concept? A limit. So what I want to do is I want to take the limit as delta x approaches 0 of this slope formula right here. F of c plus delta x minus f of c all over delta x. Okay? So as that delta x approaches 0, then I have the slope of the tangent line. Now, I use delta x to begin with because I like that change in x. However, I think delta x is hard to work with. So I'm going to offer you a different formula. The limit as h approaches 0 of f of x plus h minus f of x all over h. And all I did was I replaced the delta x with an h, because I think that's easier to deal with. And I replaced the c with x, because c represents an x value. So that kind of makes sense. So that is your formula for slope. Okay, what I'm doing is I want to move this point, this original c plus delta x point, closer and closer and closer to c. So what that means is every time I move that point closer and closer to c, my delta x is decreasing. So when I get a point that's almost right next to c right there, then that change in x is getting closer and closer and closer to 0. Here is kind of a cool animation of that secant line. Okay, so here delta x is getting closer and closer, or closer and closer and closer to 0, and that secant line becomes the tangent line right there. All right, in calculus, we have a fancy name for slope. And the slope of a tangent line is called the derivative. So when we talk about derivative, from here on out, when you hear the word derivative, you need to think slope, 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 slope. The limit used to define the slope of the tangent line is also used to define one of the two fundamental operations of calculus called differentiation. So the verb form of the derivative is differentiation. The derivative of f at x is given by this right here. Once again, here I use the delta x. I should probably change that to h. So if you would prefer, and the notation, there's several notations for derivative, but probably the most common is f prime of x. That means the derivative. So f prime of x equals the limit as h approaches 0, f of x plus h minus f of x all over h. And we've been asking you to find f of x plus h minus f of x all over h since Algebra 2. We just haven't had the limit part on it. So you know how to do this. A function is differentiable at x if the derivative exists. So that's just kind of another form of that word right there. All right, these are the most common notations for the derivative. I would say that the most common ones that you'll see are f prime of x. If your function is already written in terms of y equals something, then you would denote the derivative as y prime. And then the other one is dy dx. And what that means is the derivative of y with respect to x. So y is the independent variable and y is the dependent variable and x is the independent variable. So like if you had an equation where you had, say, h equals 5t minus 7, then another way to write the derivative of h would be dh dt. So the derivative of the dependent variable with respect to the independent variable. These two notations down here are used less frequently, but this just means take the derivative of f of x with respect to x, and this is the derivative of y with respect to x. Again, you will rarely see this fifth one right here. Okay, so let's actually find the derivative. We're going to do three different things. We're going to find the derivative of the function, then we're going to find the slope at a specific point, and then we're going to actually write the equation of the tangent line. So to find the derivative, that's where we have to use the, and this is called the limit definition of the derivative. So f prime of x will equal the limit as h approaches 0. And our formula is f of x plus h. So how do I find f of x plus h? Right. Everywhere you see an x, I'm going to plug in x plus h. And then the formula says to subtract f of x. So I'm going to subtract the function that was given to me. And then I'm going to divide by h. Thank you. I really did do that on purpose. Sometimes I do make mistakes, but I was hoping that someone would catch me there. You do need to subtract that whole quantity, f of x. Oh, thank you. And I did not mean to make that typo. Okay. All right. Now, if you were to plug in h equals 0, you would get 0 over 0. So what do we do when we have a limit of 0 over 0? Factor, solve, simplify. I'm not really going to factor. I'm going to do the other F word, FOIL. Yeah. Now, if I'm just foiling or simplifying, I haven't taken a limit yet. You have to rewrite limit as h approaches 0. No, because it all still equals each other. You don't have to rewrite f prime of x. All right, x plus h, the quantity squared. Is that x squared plus h squared? No, that's the second huge faux pas of algebra. Faux pas is a good SAT word. It's like a mistake, but it's kind of like a socially unacceptable mistake. So it's kind of a stretch to use it in terms of an algebra faux pas. All right, now, when I simplify the numerator here, a bunch of stuff starts canceling out. My x squareds will cancel. I have 3x that cancels, and I have -1 and +1 that cancel. Notice that everything left in the numerator has an h in it, so I'm going to factor an h out. So that the h's will cancel. And now I can plug in my h, and what do I get? Or plug in my 0 for h. Not yet. There is a shortcut called the power rule, but you're expected to know how to use the definition of the derivative on the AP exam, so you're going to have to humor me and spend a day on this. Okay, so that's part A. Part A is f prime of x equals 2x plus 3. Now, what this represents is a general formula for finding the slope at any point on the graph. Derivative and slope are the same thing. Part B is asking us to find the slope of f of x at x equal -1. So if f prime is a general formula for finding the slope at any point, how can I find the slope at x equal -1? All right, f prime of -1 equals 1.